So before I start talking about multiplication, I want to know how you feel about a certain logical argument. Okay, any given statement has to be either true or false. All right, so there's no kind of in between, right? If we look at like certain mathematical sentences, right? A mathematical sentence has to be either true or false. And I am going to use the logic that I am going to prove something is true because I'm going to prove it can't be false. All right, now some of you might think that that doesn't sound like good logic. All right, so I'm going to say this is true because it can't be false. All right, well, if something can only be true or false, if I can eliminate the possibility that it's false, it would have to be true. So that actually is a very sound reasoning technique. But often when students first hear me say that, they feel like, gosh, that just doesn't sound quite right. I don't know if I should agree with that. So this is where I wish we were in class and I would be asking you, how do you feel about that? And some of you would be like, I don't know if I like it. But anyway, we are going to prove the fact that -1 times -1 has to be 1. And I'm going to say that it's 1 because it can't not be 1. Okay, so again, that might not sound quite right as it falls onto your ears. But anyway, let's look at things that we already know are true. Basically, the gist of this is that -1 times -1 has to be +1 in order to fit with all the other things that we know mathematically. All right, so if we agree, and I'm sure none of you are going to disagree with me about this, that if we multiply, why isn't it letting me do this? If we multiply anything times 1, right, according to the multiplicative identity property, I multiply anything by 1, it stays the same. So we all agree on that. All right, then we also have the additive inverse property. So this is basically the college level definition that I gave you at the beginning of this segment on additive inverse, that if this equation were to be 0, then the only possible answer to A is 1. Okay, so if we were in class, I'd be saying to all of you, everybody agree, right? And I think we would all be in agreement. So anyway, here's how we're going to start our proof. All right, I am going to ask you to consider this expression, okay? -1 times 1 plus -1. Okay, and when we consider this expression, according to this that we'd agreed on, right, if I add a number to its opposite, it has to be 0. And then we also agree that 0 times anything is 0. So what I know about this expression is there's no other possible answer that I could come up with than the fact that this expression must, because of what I already know about mathematically, this expression must equal 0. Okay, so now what I'm going to do is I'm going to apply the distributive property. All right, so I'm going to come over here and I'm just going to distribute this and say, well, according to the distributive property, I know that has to be 0, and I also know that if I distribute, I get this plus this times this. Now remember, I'm trying to prove that -1 and 1 is 1. I don't know it yet. Okay, so I'm up here saying, gosh, I really don't know what -1 times -1 is. That's a question mark for me, right? And I'm not going to believe you that it's 1 until you prove to me that it's 1. So that's some unknown value. So anyway, according to what we've already agreed upon, we've agreed that this is -1. And I say, well, I don't know what this is. So how about I just call it A, because it's some unknown answer that I'm not privy to at this point. But I know that all of this has to equal 0. Well, based on what we already agreed on at the beginning, there's only one answer for A. The only possible answer for A is that A is 1, which means that the whole reason that I know that -1 times -1 is 1 is because it can't be anything else. It can't not be 1, right? Because if this weren't 1, then I'd have to disagree with something over here. Well, if I'm disagreeing with something over here, then everything we thought we knew about math just kind of starts to fall apart, all right? Because I've already established the truth of all of these. So this is a result, and again, this is a very abstract idea, right? Why should -1 times -1 be +1? But it has to happen in order to be consistent with the rest of mathematics. Now, if we want to start modeling with some of the problems involving multiplication or division, this is a place where it's a little bit harder to get, find word problems that work well, although I have a couple examples of word problems. So again, I'm going to send you to a YouTube video that's going to model how to do these with the yellow and yellow and red chips. But let's go, so actually I'm going to leave this blank. This is where you're going to the YouTube video. Let's use a number line to show that this is -6. So again, you have a number line on your paper, but I don't. But let's use the open number line approach. So what this means, 3, remember when we were doing these with whole numbers? 3 tells me the number of hops, right? So we were doing these with whole numbers back in the last chapter. So this tells me hop -2 3 times, right? So hop -2, hop -2, hop -2, here I am at -6. All right, so that's how I can use a number line to model multiplication with a positive and a negative. All right, it's a little harder to show -2 hops. So I haven't done a number line using the number of hops being negative. We also could consider a pattern approach. So patterns are a wonderful part of mathematics. And again, a negative times a negative has to be a positive in order to be consistent with other things that we've agreed upon. So if we look at this column and notice that the factors here are decreasing by 1, okay? And then the factor of -3 stays consistent. So as these factors decrease by 1, what's happening over in this column is that I'm adding 3, right? I go up 3, up 3, up 3. So if I continue to add 3, well, I have to be able to follow this pattern to be consistent with what I already have. Therefore, for consistency purposes, -1 times -3 has to be 3. I have to keep following this pattern. This has to be 6. This has to be 9. So I can use a similar rule to justify. Why don't I see this example on my paper? You guys would have it on your paper. Some of my stuff seems to have become lost in my transfer over here to Smart Notebook. Oh no, wait. On your paper, you should see something that says justify the rule A minus B equals A plus B using a pattern approach. Okay, so that's what your paper says. So if I were to start off like this and I keep on subtracting 2, and you know what? How about I switch to a text box? Because that I can type easier and faster. So right here, we're going to have next 5 minus 1, and then 5 minus 0, 5 minus -1, -1, 5 minus -2. Okay, so again, I am decreasing the subtrahend by 1. Okay, the 5 stays consistent. And what's happening over here then when I find these answers is that this answer here is 3, right? This answer is 2. Or how about, let me try this again. This answer is 4. This answer is 5. So I can see the pattern that I've got going here. As I decrease my subtrahend by 1, I increase the difference by 1. Therefore, this has to be 6. And in order to be consistent with the rest of mathematics, that has to be 7. So one more problem here, modeling using a word problem. A word problem would be nice to show why a positive divided by a negative is a negative. Oh, wait, I'm sorry. His children are positive. He's got negative amount of money, right? And I could see by the partitive approach, right, where the divisor is the number of groups, I would be putting negative $33 into 3 cups or 3 groups. Okay, and the video talks about multiplying. I didn't do anything with division, but I can see if I had 6 red chips. I feel like I should be using red when I talk about red chips. And I want to divide that by 2. Okay, so again, right, there's my negative 3. There's my negative 3. All right, so that would model well. Now, if I want to show this division problem using the measurement subtractive model. So remember what that means. That means continue to measure off the divisor until we get to 0. Right? Well, look at what happens if I keep measuring off negative 4. Right? I'm saying how many negative 4s can I take out of negative 20? Right? So if I had 20 negative chips, 20 reds, I could take out groups of 4 reds, and then the number of groups that I would have until by the time I got to 0 would be 5. All right, so I could show it this way, that I have 20 reds, measure off 4 reds, measure off 4 reds, 4, 4, 4. I have 5 piles of 4 reds. All right, it would be harder to model if I'm dividing by a negative. I mean, how do I talk about negative 2 piles, right? That doesn't really make sense. But luckily, when it comes to division, we have always got our missing factor approach. And since we've agreed on lots of facts about multiplying positives times negatives, right? We've already agreed that a negative times a negative has to be a positive because it can't not be a positive. So we always can model something and justify an answer to a division problem by using the missing factor approach. So please review the next YouTube video where you'll be looking at modeling products using the blue and yellow chips. Thanks.